As we finish setting up, I want to introduce our next speaker, Ekrem Esmer. He'll be talking to us about constraining the occurrence circumbinary planets through eclipse timing variations.
Hi, I think you can hear me right now, right? Sorry for the typo, it should be occurrence rates. Is this working? Oh, sorry. Yeah, occurrence rates. I'm Ekrem from Washington University in St. Louis. I'm a postdoc working on exoplanets, binary stars, and orbital dynamics of those systems. And today I'm going to talk about one of the projects that I currently work on constraining the occurrence rates for circumbinary planets and brown dwarfs with eclipse timing variations. Okay, so circumbinary planets are planets orbiting a binary system, and they're also known as p-type binaries here. And I guess the reason Johann Netesky did not mention circumbinaries in the landscape of exoplanets are they're extremely rare. So the total population reach almost exceeded actually 6,000 exoplanets right now, and less than 1% of them are in fact circumbinary planets. And around 8% of them are planets around a single planets around a star that belongs to a multiple stellar system. So the majority of those planets that we currently know of are around single star systems. And this is somewhat contradictory to what we know about stellar multiplicity. The majority of the stars should belong to multiple stellar systems, but apparently that's not the case for circumbinary planets. And sorry for that again, these two should be animations, but I uploaded the PDF version of my talk forgetting that. The thing is, circumbinary planets have very exotic cases like planets around post-common envelope eclipsing binaries or polar orbits. This animation was showing two stars going through the stage of common envelope, and the aim was to making you questioning like how a planet can survive or form in this complex environment, but I think you can do it with your imagination. And there are some other exotic cases where the planets have polar orbits, meaning that the eclipsing binary has an orbital plane, but the planet's orbital plane is perpendicular to the binary's orbital plane. These objects are very interesting in terms of their formation as well, because for circumbinary planets, you may have shorter disk lifetimes or truncation and warping. And they're also very interesting in terms of their dynamics, because you have two massive objects orbiting each other in the center, creating stability boundaries and stirring of planetesimals, which affects their formation. So what we know about their occurrence rates, they're not that much study in the literature up to now. And there are two major ones. One is based on transits, the other one based on radial velocities. So this study that was based on Kepler transits was more than 10 years ago. And they found the occurrence rate for planets between the sizes of more or less Neptune and Jupiter within 300 days or shorter orbital periods to be 10%. And the other study that based on radial velocities, they used the Bebop RV survey, and they were able to provide an upper limit on the occurrence rate of those objects. And for super Jupiters or Jupiter-like planets between 1.5 and 13 M Jupiter, they were able to set the upper limit to something around 6 and 10% or less. And for the brown dwarf circumbinaries, that occurrence rate upper limit was 6.5, and all these values are within 2 sigma confidence level. So what is the motivation of our project? Is that there is poor overlap between the detection methods if you want to search or detect circumbinary planets. especially the transits, the blue ones here, and the rest, the eclipse timing variation ones. There's almost no overlap, meaning that if you detect a planet with, let's say, transit, it is very unlikely for you to confirm that detection with eclipse timing variations. So this means that if you run an occurrence rate based on transits, then probably you won't have any idea about the occurrence rate of planets that can be detectable with eclipse timing variations. Most of the current estimates are mostly upper limits, meaning that there's lots of things to do on the occurrence rates. And there is no occurrence rate study based on eclipse timing variation, so this will be one of the first, I guess. So we structured this work into two major parts. One is the survey part, where we wanted to detect as much as possible of such objects, and the simulation part, where we wanted to understand the efficiency of the methodology that we applied. And in the survey part, our target sample was 152 detached eclipsing binaries curated from test eclipsing binary catalog, and we used their test data. We modeled them with LS-Fitter, which is a tool that you can model transit, radial velocities, and many other things. And we did the same thing with generalized Gaussian models, and with these two methods, we determined their exact eclipse mid-times and built eclipse timing data for our targets. In general, these two methods agree well with each other, with some slight differences as well. We produced the eclipse timing data for our targets and run Lomskargel search to see if there are some cyclic trends. And we used false alarm probabilities as signal significance. And we found 19 of those targets to have false alarm probabilities less than 1%. And in 6 cases, this is 6, the 6 cases, the hypothetical third mass should be below the stellar mass limit of something around 80 Jupiter mass. But in 5 cases, the observed variation is due to either stellar activity or apsidal motion, or probably something instrumental. But for 1 case, the reason for this variation can be due to activity as well. So this may be a false positive, or maybe due to an object with a low mass brown dwarf. It is yet to be confirmed, and we need some further investigation on that. For the simulations part, since TESS is not observing the whole sky with the same frequency, we had to build our binary population based on Gaia stellar sources. We generated our synthetic circumbinary systems by randomly sampling the binary and the circumbinary components from related probability distributions, and generated 4 million systems and simulated the test data. This also should be an animation, but it's not working right now. We simulated their test data and ran the same thing, Lomskargel search, and we found that the recovery rates for circumbinary brown dwarfs should be between 3 and 6%, and that value for super Jupiters should be around less than 0.1%, meaning that TESS is not the best data source that you can utilize if you want to search for Jupiter-like planets and use eclipse timing variations. The occurrence rate were estimated for brown dwarfs in 2 cases, in case of no detection, assuming that the single object that we detected somehow is not an actual detection and a false positive. Then the upper limit should be 40% in 2 sigma confidence level. If that is an actual detection, then the occurrence rate should be 13% for brown dwarfs, circumbinary brown dwarfs. However, we were not able to constrain the occurrence rate for super Jupiter since the recovery rate was very small. So, continuing on that result, what we're planning to do is for brown dwarfs, we are planning to increase the target size to around 10,000 targets, curating a few eclipsing binary catalogs. And we have some preliminary results for something around 12,000 targets. For 2,000 of them, we were able to detect signals with false alarm probabilities less than 1 per million. So we have thousands of targets to investigate. And for super Jupiters, since test photometrical precision is not enough, we'll go back for another source, which will be the Kepler photometry with higher precision. And we are planning to determine the ETV yield for future observatories like Plateau, and maybe with a combination of Vera Rubin as well. And most of the things that I talk about here was accepted to publish in AJ, and here's the QR code, scan it if you're interested, and if you have any questions or comments, feel free to reach out, and I would like to thank you all for your attention.
Questions for Ekrem?
Hey, Zachary Hartman, NASA Ames. So for your for the binaries that you were simulated, did you have any limit on the periods that you had for your systems? Like, did they have
Period limits.
what model did you use?
Yeah,
for any?
period limits of the synthetic binaries, right?
Yeah.
We sampled the periods of those. Well, I think I have the image for that. Yes, we had. Here you go. And this is the distribution of the periods of the binaries. And those distributions were based on test eclipsing binary catalog because it has thousands of eclipsing binaries. So we build a probability distribution based on that, and we randomly sampled from that. So whatever test eclipsing binary catalog has, we also have. But you can see it's more like around, it starts from 1 days to something a bit more than 100 days.
So for your short period systems, did you take into consideration the possibility of a third star in the system at
No,
some
we
point?
did
Or,
not.
okay.
No.
Awesome. We are out of time, so let's thank Ekrem one more time.